So thank you for coming, Bret.
Thanks, Jeff. Okay, enough of that. So, say you're a scientist. So you're a scientist, you're working on like really important science, and you're doing your experiments and you're getting back data. You need to understand this data, and you know that one of the best ways of understanding anything is to turn it into a picture. So you're a scientist and you need to visualize this data, and today you have three options for doing that. One thing you can do is to use a chart generator like Excel, MATLAB, R, where you put in your data, you press the bar chart button, it gives you a bar chart. Option two is you can just draw a picture using pen on paper, using an Illustrator, Photoshop, a direct manipulation drawing tool like that. Or option three is that you can write code using D3 or processing or OpenGL or anything like that. You write code and that generates a picture. So you're a scientist, you need to visualize your data. Those are the three options you have, and all three of these options have big problems. And I believe that being limited to these three options is limiting the thoughts that our creative scientists can think. So let's take a look at each one of these, starting off with something like Excel. If you want a bar chart, Excel will give you a bar chart. If you want a scatter plot, Excel will give you a scatter plot. But as a creative scientist, you don't want a bar chart or a scatter plot. What you want is freedom. What you need is the flexibility to create the pictures that best represent your thoughts and your ideas. And that's not going to fit into some generic form like a bar chart or scatter plot. So here's an analogy. Imagine you're a scientist and you make some amazing discovery and you want to write a paper to communicate your discovery. So you fire up Microsoft Word and it gives you the scientific paper template, which is a completely pre-written scientific paper, fixed structure. All you have to do is play Mad Libs and fill in the blanks with the details of your work. This would be absurd, right? We can't convey our thoughts and ideas in a fixed structure like this. We need the freedom to be able to create our own sentences. And that's really exactly the same situation as this. It's this completely fixed structure, and you're just kind of filling the blanks with your data. This might seem like a far-fetched analogy because we all understand the expressiveness of language. We all understand, of course, we have to be able to write our own sentences. But I think culturally, we don't really understand the expressiveness of information pictures. I think a lot of people think, well, how many types of visualization are there? There's like 4, right? And it's kind of a meaningless question to ask like how many types of visualizations there are. It's like asking how many pictures are there? How many sentences can there be in the world? Every idea can have its own unique sentence. Every thought can have its own unique picture. Richard Feynman revolutionized our understanding of quantum physics with these diagrams, which became known as Feynman diagrams. He didn't just like go to Microsoft Excel and find the pull-down menu that said Feynman diagram. He invented these things. So in the same way that we invent every sentence that we write, we need to be able to invent every picture that we draw to explain our thoughts. So these chart generators, let's forget about them. They're not expressive enough to allow us to explore our ideas. So that brings us to the next option, which is drawing a picture. This is basically the only option 30 years ago. 30 years ago, every scientist, engineer, they had their stack of graph paper and they had their pocket full of pens, and when they wanted to see a visualization, they just kind of drew it out. And there's this wonderful freedom and directness to drawing. So, let's say, for example, I run my experiment and I get back some data, and so I can say, well, there's these two variables which seem kind of related, so I'm going to plot one against the other as a kind of scatter plot like this. But the order that these samples were taken also matters, so I'm going to connect them up with a line like that. And each one of these samples actually has a width, a radius in one of the variables, which is kind of different for every sample, which I kind of need to see like that. And for this experiment, it's important to know whether these widths actually cover the entire range or if there's gaps. So maybe I'll take this and kind of, fill in that, and that sample covers that range, and that one covers that range, and kind of do it like that. And, I can see, okay, there's this gap right here that wasn't covered by any sample, and this gap right here. And Excel can't draw that. This doesn't even have a name. It's just something that kind of came out of my thought process. So being able to do this kind of direct drawing is, it's really flexible, really expressive. The downside, of course, is that you have to draw this by hand. So if I get a new data set, I have to crumple this up, throw it away, draw it again. If I want to look at a log scale, or like this should be green and that should be red, throw it, I crumple it up, throw it away. Also being forced to draw everything by hand kind of puts an upper bound to the complexity of our pictures. We're only able to explore things that are kind of enough for us to draw by hand. Of course, nowadays, nobody uses graph paper anymore. We all use computers, and we have similar direct manipulation drawing tools, things like Photoshop and Illustrator, where you can create that same picture, but it has exactly the same downsides that when you're drawing it in Illustrator, it's a one-off for that particular data set. You get new data, you have to throw away your Illustrator file and draw it again. So that brings us to the third option, which is coding. So we say, we can't have these static pictures that we're drawing in Illustrator. We need something dynamic. We need a dynamic picture where we get new data and the picture changes. And as soon as you say that, as soon as you say, I need dynamic behavior, I need something that changes, you have to throw out all of your direct manipulation tools and start working in this stuff. As soon as you say, I need dynamic behavior, then you're no longer drawing, you're programming. And here's a definition of programming, which I kind of like. Programming is blindly manipulating symbols. And this is a very precise definition. There's two parts to this definition. One, blindly, meaning that we can't actually see the picture that we're drawing. So that code in the background might draw that same chart I was showing, but I don't see the chart. When I'm writing this code, I have to imagine the chart in my head. You can't actually see what you're doing. So we're working blindly. We're also manipulating symbols instead of manipulating the picture itself. If I wanted to add something to that chart, like if I wanted to add marginals, I would just take my pen and add marginals in the margin. Here I'd have to find the right code. I'd have to figure out what variables are doing what. It's very indirect manipulation. I'm not directly manipulating the picture. I'm indirectly manipulating it through this layer of symbols. There's these visual languages which aren't any different. Quartz Composer or Max MSP or Scratch. You're still blindly manipulating symbols. You can't see the picture, and you're not directly manipulating the picture. So I don't care whether your symbols are in text or they're in little boxes you drag around. You're still blindly manipulating symbols. So those are the three options that we have available today. So you're a scientist. You want to visualize your data. You can use one of these chart generators that's not expressive enough to let you explore your thoughts. You can draw a picture, but it's not dynamic. Or you can code up a dynamic picture, but you're not drawing, you're blindly manipulating symbols. So what if there was a fourth option? What if there was a way of creating pictures through direct manipulation, but pictures that were dynamic? So something like, I have my data, create some variables here, and drag in some data. And say, I kind of want to initially just plot them one against the other like a scatter plot, so I'm going to draw a rectangle here and scale the width by one of the variables and scale the height by the other variable. Put a little dot here at the end. And I want to iterate that across all of them, so I just loop that, and it goes through and does that and does that and does that, and now we have our scatter plot, except I want to connect them up with a line so I can see what order they're in. What I'm going to do is draw a line from the previous sample to the current sample. I want it to be orange. Then there's the range associated with each sample, so I'm going to draw a line and scale it by that width and plop it over there on the sample. So now I can see the widths, and I'm going to put little wings on them. And then I want to be able to see whether these are covering the entire range, so I'm going to draw a rectangle and move the top of the rectangle to the top and the bottom of the rectangle to the bottom. Let's get rid of the stroke there and make it orange. And so now I can see there's these gaps here that weren't covered, and then there's this part here that was covered by two of them. And then I can say, well, I'm kind of losing track of the order that these are going, whether it's going in that direction or going in that direction. And maybe instead of connecting them with lines, I should use arrows. So I'm going to just draw an arrowhead. I'm just kind of freehanding it here. And plop it over here on the sample point and rotate it by, rotate it by whatever the angle of that line was. And so now I've got my arrows. Oh. Make them orange. Maybe scale them down a bit so they're a little more slim and tasteful. And the circles are just clutter right now, so I'm just going to select the circle and get rid of it. So I created this thing by direct manipulation. I created this thing by directly manipulating geometric objects on the canvas, just like using Illustrator. If I want to add anything to it, like say I want to see some marginals, I just take the line tool and I draw my marginals. And if I want to see marginal on this side, I just draw the marginals, and there they are. I didn't have to ask Microsoft's permission to see my marginals, and I didn't have to find the right code to type in to see the marginals. I just drew them with the line tool. So direct manipulation drawing, just like using Illustrator. The only difference here is this was driven by data. So I drag in a new data set, the picture changes. Drag in a new data set, the picture changes. Or if I go into the data and just dial this number up and down by hand, the picture changes. So direct manipulation drawing, but it's driven by data and parameters. In the second half of the talk, I'm going to talk a lot more about how this tool works. But first, I want to talk a little bit more about why it matters. Actually, I'm going to let Alan Kay talk a little bit about why it matters. Here's Alan circa 25 years ago.
Some interesting work in the literature of creativity. One of them was by Jacques Hadamard, the famous French mathematician, who in the late stages of his life decided to poll his 99 buddies, the other who made up together the 100 great mathematicians and physicists on the earth, and he asked them, how do you do your thing? And they were all personal friends of his, so they wrote back depositions. And only a few out of the 100 claimed to use mathematical symbology at all. It was quite a surprise. All of them said they did it mostly in imagery or figurative terms. And an amazing 30% or so, including Einstein, were down here in the mud pies. Einstein's deposition said, I have sensations of a kinesthetic or muscular type. Einstein could feel the abstract spaces he was dealing with in the muscles of his arms and his fingers. You see, the sad part of Hadamard's diagram is that every child in the United States is taught math and physics through this channel. The channel that almost no adult creative mathematician and physicist uses to do it. And that is really a shame. They use this channel to communicate, but not to do their thing.
So if Alan's right that our great thinkers do their thing in pictures and not in symbols, then we can't force them to go through a layer of symbols to draw their pictures, right? Here's a page from one of Feynman's notebooks where he's working out the beginnings of quantum electrodynamics. Feynman was one of the great symbol manipulators of our time. He was renowned for the integrals he could do. And yet all of his creative work came out of this kind of mental imagery. And you can see right here, he's kind of like doodling on his note papers, kind of figuring things out in pictures. And he would talk about how he would solve a lot of problems using pictures and then kind of bring the mathematical formalism into it after the fact to kind of justify what he had figured out in pictures. Here's the late mathematician Bill Thurston, who wrote, "People have very powerful facilities for taking information visually or kinesthetically and thinking with their spatial sense. On the other hand, they do not have a very good built-in facility for inverse vision, that is, turning an internal spatial understanding back into a two-dimensional image. Consequently, mathematicians usually have fewer and poorer figures in their papers and books than in their heads." So what this means to me is that as tool makers, we have to do everything we can to get those pictures out of their heads and into the world. And if what Alan Kay is saying is right, that these people are thinking in pictures, we can't force them to take a detour through symbols to get to their pictures. They need to be able to get directly to the pictures through direct manipulation drawing. So I'd like to give you a little demo of this tool that I've been playing with for doing direct manipulation drawing. And first I want to say that I'm not necessarily saying that this is like the right way of doing this sort of drawing. I'm not saying this is the future of it. This is kind of a starting point. So one analogy might be Fortran in the 1950s. Fortran was the first high-level computer language. It was the first language where you worked with mathematical expressions instead of individual machine instructions. And it was totally revolutionary, but we've come a long way since then in programming language design. We can look back at Fortran 1 and say, like, it was totally wrong. It didn't have subroutines. It didn't have conditionals as we know them. It was kind of relentlessly imperative. But it was a starting point. It was kind of this simple and straightforward starting point that could grow into everything we know about programming languages today. And so that's kind of what I'm aiming for in this project, is not to necessarily to find the right way of doing dynamic drawing, but to provide a starting point where we can explore what it means and what can be done with it, and then we can figure out how to do it best, maybe over the next few decades. So here's how this tool works. There's this section up here labeled pictures, and these are just where I have the pictures that I've drawn. I can select them and edit them. And then the picture I'm editing has a sidebar over here, and there's 3 panels in the sidebar: data, steps, and measurements. And you can think of data as the input to the picture, and then steps is a procedure that we go through to generate the geometry, and then measurements is kind of the output of the picture. So input, procedure, output. The best way to think of this data panel is it's kind of a little spreadsheet where you can like work with numbers and get the numbers you need to generate the geometry. To take a particular example, let's say that we're analyzing a solar power installation. So we've got this solar power system, and it has a number of panels. It has 600 solar panels. So I'm going to create a variable called panels, and it's 600. And we're going to be generating power kilowatts per panel, and say 0.2 kilowatts per panel. And so our total power in kilowatts is going to be the number of panels times kilowatts per panel, which is 120. So we're just defining these variables as expressions, and these are constant expressions, and here's an expression that depends on other variables. It's all completely declarative, like a spreadsheet. When anything changes, all the other things change. The order doesn't matter, it just follows dependencies. These are scalar variables, and then down here we can have array variables. Here's the default one that was given to me. It's just an array that has 1, 2, 3, 4, 5 in it. I can like drag this off and use the current value of the array, or I can hit on this little triangle, and these are different reductions that I might want to use. Get the minimum item, the maximum, the sum of them, drag those off and use it. For this particular example, the solar power example, our power here in kilowatts is the power we're generating if it's sunny. Now, it's not sunny all the time. Different months of the year have different number of hours of sunlight. So why don't we create a variable called sun hours? It's hours per month, and we're going to drag in some data from a place in San Francisco. So we can see in January we get 53 hours, and February 86, all the way over to December 65. And then we can say the amount of energy we're generating in kilowatt hours is equal to the power in kilowatts times the number of hours, and we get that. And then we can say, well, those numbers are kind of big, so why don't we convert them to megawatt hours instead? So energy in megawatt hours is just equal to the energy in kilowatt hours divided by 1,000. So in the same way that I'm working with scalar expressions, I'm working with array expressions. I can add arrays together, add them to scalars, that kind of thing, and everything kind of works out. So this data panel, we're working with numbers. It's completely declarative. The order doesn't matter. It just follows dependencies and figures things out. And we're specifying things using mathematical expressions. And now the steps part, where we're going to generate the picture, is exactly the opposite. It's going to be completely procedural, not declarative. And we're going to be specifying pictures by directly drawing them on the canvas using drawing operations. And the drawing operations are over here in a little cheat sheet. We can do things like draw a line, draw circles, we can draw rectangles, we can scale things, rotate things, and really that's about it. Everything we're going to do just comes out of those basic operations of drawing shapes, scaling, and rotating them. This is just like a standard vector drawing tool like Illustrator with just two extra ingredients. The first one is that every drawing operation we do records a step over here in this procedure. So you can see I drew a line, I drew a circle, I drew that rectangle, I scaled it. Everything I do records a step. You can see the step it recorded up here, scale rectangle around its top left by 72%. If I don't want it to be 72%, I can use the scale tool and just change that. I can also go up here and just drag that number up and down. Or it can be an expression. So I can say, well, maybe I should scale it by whatever the number of panels is divided by 500. So now it's an expression driven by this data. When the data changes, that scale is going to change. So that's how we're getting dynamic geometry. These steps that we record can be parameterized by data. So that's kind of the first extra ingredient. The second ingredient has to do with snapping. When I start drawing these little yellow dots up here on the canvas, and I can snap to like the bottom of the circle or the bottom of the rectangle or anywhere I like. This is totally standard. Every drawing tool in the world has snapping. Here it's used in kind of a special way. So here when I snap to the bottom right corner, the operation that it's learned is draw a line from the canvas's bottom to the rectangle's bottom right. That means it's going to draw the line to the bottom right of the rectangle wherever that bottom right happens to be. So if the data changes, then the size of the rectangle is going to change. Then where the line is drawn is also going to change. So snapping is how we establish relationships between the geometric objects. Let's go back to our solar energy example. We have here this energy in megawatt hours across the year. Let's start off trying to visualize that with a simple bar chart. So what I'm going to do is I'm going to draw a rectangle across the canvas. And I'm going to scale down that rectangle to be the width of one bar. If there's 12 data points, it should be scaled by 1/12. Except there's 12 data points right now, but maybe later I'm going to add more data, remove more data. So it really should be 1 over the number of data that we're plotting. So I have this rectangle here, and I've turned this rectangle into a guide. That's why it's in blue. And an object that's a guide doesn't show up in the final picture. It's just a temporary variable. It's something I'm using to construct the picture. So I drew that guide, and now I'm going to fill it with a rectangle just by drawing a rectangle from one corner to the other. And that's going to be a bar. I'm going to scale down that bar by whatever the current data is divided by whatever the maximum is. So whatever the maximum in that array is going to get scaled to the top of the screen, and everything else is kind of scaled proportionally to it. So I drew my rectangle, I scaled it down, and now I'm going to take this guide and plop it over next door. And now I just want to do that again and again and again. So I just select those 3 steps where I filled the rectangle, scaled it down, moved the guide over, and I loop that. So it's going to fill it, scale it, move over, fill it, scale it, move over, and so on and so on and so on, all the way through, and now we have a bar chart. You'll notice that the way I'm going through that procedure, I'm hitting the up and down arrow keys. So I'm like starting here, hitting down arrow, down arrow, down arrow. If I hit down arrow here, it loops back around because up and down is actually following the trace of the dynamic execution of the procedure. So that way, if I don't understand how a picture was drawn, I can just follow exactly what the computer was doing and see, okay, here's the step where things kind of messed up. So I can go up and down through each individual step. I can also hit left and right to go to previous and later iterations staying on the same step. So I can go up or down, left or right, and that really lets me quickly navigate through and understand the execution of this procedure. So I've drawn my bars. Now I think I'd like to label them with the values. So I'm going to just use the text tool and draw some text across the top. And that's the default string. I'm going to double click on that to bring up the properties. So here's are the different text properties, like the text and the color and that sort of thing. And you'll notice that this is in a panel labeled data, which kind of looks like the panel over here labeled data. And that's kind of a little hint as to how things are going to work when we're embedding pictures inside other pictures. So I'm going to change this text to whatever the data point is. Make that a little bit smaller. And turn down the opacity of it. Drag it down a little bit so inside the bar. Now something I want to do is, I don't like having this bar scaled all the way to the top. I'd kind of like to be able to specify my own top. And so I'm just going to create a new parameter over here. I'll call it top megawatt hours and say maybe it's 20. And then go back to this part where I was scaling the bar by the energy divided by the max energy. Instead of max energy, it should be whatever this top is. Now I have a parameter where I can dial that up and down, and it's scaling the entire chart. Now let's say that there's a second solar power installation that we want to analyze. So now let's say instead of just looking at one bar chart, we want to look at a chart that has pairs of bars so we can compare these two sets of data. And so what I'm going to do is I'm not going to draw this whole thing again. I'm going to create a new picture. Then I'm going to put that bar chart inside this picture. So in the same way I can use the rectangle tool to draw a rectangle, I can use the picture tool to choose one of these pictures up here and then draw it into my picture. So I drew that picture, and then I would want to draw another picture on top of it, but I don't want it on top. I kind of want the bars to be skinnier and like have pairs of them. So I'm going to go back here. I'm going to select this bar and kind of scale it down a little bit to make it skinny. So now I have a bunch of skinny bars. And then the last thing I want to do is I want to be able to expose the color of this bar so I can change it from the outside. So I'm going to create a new parameter out here called color. Drag it into the inside. So now what that means is that I have this color parameter out here, which I can change and change the color of the bars. So now I can go back to here, and I've got this picture with these skinny bars, and I'm going to draw another bar chart on top of that, and I'm just going to move it over by a little bit. So now we have these pairs of bars, and I'm going to use that color property I just exposed to change the color so I can tell them apart. And now I want to give it different data. So you'll notice when I double click on this picture I embedded, the properties that came up were exactly the ones that I was defining over here on the original bar chart. And I can change them. I can override any of those properties. In this case, I actually want different data. And so what I'm going to do is I'm going to drag in the data from this other solar power installation and drop it in. Now we have two bar charts side by side as a pair. This was kind of a quick introduction to the sorts of things that you can do with this tool and the way that you work by using this dynamic geometry. I kind of want to wrap up by showing a quick video of drawing a lot of different standard chart types, just to show that a lot of things that you normally would be doing in Excel or D3 can be drawn directly pretty easily. Starting off again, drawing a bar chart, same way as I did before. You notice that all the things I'm creating here, because you can embed them in other pictures and you can override their parameters, they can be used as components. So I drew a bar chart, and now I'm going to be drawing two bar charts, one plotting the sum of two arrays in the background, and one plotting another array. And that effectively looks like a stacked bar chart. So I can adjust the pink, or I can adjust the blue. I'm going to draw a line chart, which is exactly the same as a bar chart, except I just hide the bar and draw a path from one bar to another. So there I'm drawing the path. I'm going to turn off the fill. Here I'm playing with the data just to show that it's all dynamic. A multi-line chart is just two line charts on top of each other. For the area chart, I'm going to just duplicate the line chart and add the fill and close up the path. And now I have an area chart. And now I'm going to make a stacked area chart the same way I did as a stacked bar chart, just plotting the sum in the background and then one of the arrays in the foreground. Pie chart. So I'm going to draw the circle, I'm going to draw that line, and that line's going to rotate around the circle. I'm going to just draw a path, kind of trace a path around that wedge. And the color I'm going to use is going to be dynamic. It's going to use an expression so that every wedge has its own color. Donut chart, pretty similar. I'm going to draw a line. I'm going to come inside the line, draw the inside of the wedge, come out, trace out the outside of the wedge, move the control point, specify the center of the arc, give it a color, and iterate. And I made it so you can control where it was cutting into that line to control the size of the hole. A grid. I'm going to make a little rectangle there, and I'm going to basically use a straight edge and like draw lines off the bottom of it. And then draw lines off the right side of it. Now when I change the size of that rectangle, it's changing the pitch of the grid. So I'm specifying the pitch of the grid geometrically with this rectangle. And this one's a little bit different. Here, I'm not going to use data. I'm going to do a simulation of a dynamical system geometrically. So that line represents the position and velocity of a particle. I'm moving it with some velocity. I'm scaling it down to represent damping. And then I'm pulling it in towards the target. This is actually an implementation of the spring equation, specified entirely geometrically. There's the path. I'm going to turn off the fill and turn on the stroke so you can see it. And then I'm going to change the initial velocity and change the stiffness of the spring, change the damping. So I didn't talk about that sort of thing very much in this talk, but there's another talk I've given called Stop Drawing Dead Fish, which deals a lot more with this sort of simulating dynamical systems using geometry. So to sum up, you're a scientist, you're doing experiments, you're getting data, you need to visualize that data, and today your three options are to use a chart generator like Excel, which doesn't have the expressiveness to allow you to explore your thoughts. You can draw a picture, but it's not dynamic. Or you can code up a dynamic picture, but then you're not drawing, you're blindly manipulating symbols. And if Alan Kay is right, that all of our great thinkers think in pictures, not in symbols, we can't force them to make a detour through symbols to get to their pictures. We need direct manipulation drawing of those pictures. And so what I showed you was one approach to that, the kind of interactive dynamic geometry approach. So the tool I showed you, it's basically a spreadsheet and a drawing tool kind of stapled together. The spreadsheet part and the data section where you define variables and they're all calculated declaratively. And then there's the drawing part, which is exactly the same as Illustrator. The only two differences are every drawing action creates a new step, which can then be parameterized by data. And snapping becomes really important. Snapping is how you express your intent, how you express relationships between geometric objects. So to address the inevitable question, this tool will be on the web and will be on GitHub and all that before long. But I'm hoping that this talk will inspire you to think about dynamic drawing, to think about what can be done with dynamic drawing and what it means for creative fields like science. And maybe even kind of hint at the larger concept of how do we create dynamic behavior in general? All the things we do on the computer, are there ways to do that through direct manipulation instead of blindly manipulating symbols? Thanks.